Right, so this week we're going to complete the first major algorithmic design paradigm, namely divide and conquer. We sort of did the basics, so now we're going to do some more advanced stuff. And so I have one lecture on each of two things. So today is about the master method. And this will be basically kind of, the mother-lode recursion tree argument. Okay, and it's going to solve a lot of questions very easily, including the ones we had for integer multiplication. The one kind of drawback the master method has is it works when all of the subproblems have the same size. All of your recursive calls are invoked on the same fraction of the input. That's usually the case, but I want to show you an algorithm on Thursday where there's actually unbalanced subproblems, namely linear time selection. And so in the course of discussing linear time selection, we'll also kind of do a brief discussion of something called the substitution method. Okay, so that'll be Thursday. And both this lecture and the next one, they're not super mathematical, but they're probably above average for 161, which I recognize many of you already probably view as a relatively mathematical class. But I want to sort of say this over and over again, so that it's clear, is never in 161 are we going to be doing math for math's sake. That's never going to be the point. It's just a fact of life that you come up with ideas that seem really cool, and it's just really hard to tell whether or not they work. And yeah, you can code them up and sort of simulate them and sort of hope you can extrapolate. But if you really want to understand why something works or why something does not work, typically you need non-trivial mathematical analysis. Okay, and so that's what I'm going to be showing you this week. Okay, so cool algorithmic ideas, often, there's no way around it, need non-trivial analysis to evaluate. Okay, and we're still sort of in this cliffhanger situation where we have no idea if a recursive approach to integer multiplication is better than the grade school algorithm or not. And if so, why? Okay, so quick review from lecture 1 before I get around to stating the master method. So where were we? Grade school multiplication of n-digit numbers takes, if you think about it, really theta of n squared time. Okay, for each of the n digits in one of them, you do n operations, and then you do some additional additions. And the recursive approach for the proposal was to write x equal, to basically split it up into n-digit numbers. Where here A, B, C, D have n over 2 digits. And then just expanding, x times y is equal to AC with a shift, the sum of AD and BC with less of a shift, plus the product, or plus BD. Okay? And again, I'm going to call this star. Now we have two algorithms. The first one was to recursively compute the relevant four products, namely AC, AD, BC, BD. And then what you got to do, then you just got to append some zeros and do some additions. Addition, if you think about it, it's pretty clear it's linear time. So then compute star. So that was the more obvious algorithm. And so let's write down an expression which in some sense expresses what the running time of this algorithm is going to be. Okay, and so for this we need to use a recurrence. I hope all of you have seen a recurrence before. They're going to be really important this week at least. But let me remind you. So T of n, as usual, is going to be a function describing sort of the worst case running time of an algorithm on input of size n, or in this case with n-digit numbers. Okay, so this is a definition. We're defining capital T. And what it's supposed to denote is the worst case runtime of this algorithm for n-digit numbers. And because it's a recursive algorithm, we're actually going to define this function capital T in terms of itself. Okay, in terms of capital T invoked on smaller natural numbers. So that's what a recurrence is. So you express T of n in terms of running time of recursive calls, plus the work that is not in the recursive calls. Okay? So for this algorithm, and for something that's defined recursively, whether it's an algorithm or it's a function, you better have a base case. And as usual, the base cases are sort of not, you need to write them down, but they're not interesting. So what's the worst case running time of our algorithm when I give you one-digit numbers? Well, it's bounded above by a constant. Okay, again, maybe this is 1, maybe this is 2, maybe this is 3. It kind of depends how you count operations. Like, do you count the comparison, checking you're in a base case? Do you count sort of the return as an operation? But as we discussed Thursday, we've set up this formalism exactly so that we don't get sort of sidetracked on these irrelevant detours. Okay, so the point is, when you get to the base case, you have two one-digit numbers. It takes a constant number of operations. What that constant is won't really concern us. Some small constant. So I'm going to be a little sloppy about this on purpose. On the other hand, if you're not in the base case and you have to recurse, then we define the worst case runtime, or we can relate the worst case runtime for n-digit numbers to the worst case runtime for smaller numbers. Okay? So in general, for a recursive algorithm, you want to think, okay, what do I do in the recursive calls? What do I do outside the recursive calls? Well, in the recursive calls, first of all, we have 4 of them. Right, so there's going to be a 4 here, because we recurse 4 times. Now, how much work do we do in each recursive call? Well, we're not going to do anything more than the worst case running time required to multiply n over 2-digit numbers, because that was the size of the numbers we passed to each recursive call. Okay, so here's defining capital T recursively. Okay? So that is work done by recursive calls. Okay? Now, we also have to do some stuff outside recursive calls. Namely, given, once we get back the value of AC, AD, BC, and BD, we have to compute that expression star. What does that require? Well, we have to do an addition. Again, I want you to think about this, but that's linear time, if you think about it. And then we append a bunch of zeros, and we append a bunch of zeros. And those are also linear time. So not counting the recursive calls, there's a big O of n here. Okay? So this is, it's certainly the first example you've seen this quarter. This is how we're going to express recursively the running time of this recursive algorithm. Now, this is not itself directly useful. What we want to know is what is the overall running time of this algorithm, just period, without this recursive business. Is it n squared? Is it n cubed? Whatever. I'll give you the tools to compile a recurrence like this, which is not directly useful, into a running time bound, which is directly useful. Okay, that's coming up. But for now, I'm giving you the vocabulary of how do you, first of all, express running times of recursive algorithms, and that's using these recurrences. Okay? So we also had this second algorithm using Gauss's trick, which uses only 3 recursive calls. Very clever. So recursively compute AAC, BD, and A plus B quantity times C plus D. Now the observation from lecture number 1 was if you take this and you subtract each of these, you get that middle coefficient that we care about, AD and BC. So it's a technique, it's a trick for giving us the value of what we really care about, the sum of AD and BC, without having to separately compute quantities we don't actually care about, AD and BC, separately. Okay. So how is this recurrence going to differ from the one in for the first algorithm? What's going to be different? Here's the hint, not very much. So what? Yeah, so all you got to do is like decrement one of the numbers there. Right? Everything's the same except you replace the 4 with the 3. Okay? Now, what is true, if you think about it, is that, you're still doing a linear amount of extra work. It's a little bit larger, so the constant factor in the big O is going to be a little bit bigger here. But as we'll see, that's not going to matter when we get into the master method. Okay? So again, if n equals 1, or let's see, what an eraser. So new recurrence. So again, we have t of 1 at most a constant. And now we have t of n at most 3 recursive calls, each again on input sizes of basically n over 2 digits, and again with a linear amount of work outside. Basically just additions and shifts. Okay? So, all right, so we changed one recurrence and we dropped it from a 4 to a 3. So let me ask you, so what if we did it again? We don't know how to do it in the context of multiplication, but just for discussion, what if I replaced that 3 by a 2? Would that be a recurrence of an algorithm with which you're familiar?
Is that just merge sort?
That would be merge sort. Right, so merge sort would have exactly the same recurrence, except that 3 would be with a 2. Right, we recurse twice on the left half of the array, the right half of the array. So each subproblem size is n over 2. And remember, we analyzed the merge subroutine, and that took linear time. Okay? So at this point, we can do sort of like qualitative things about what the running times of these algorithms might be. So like this algorithm number 2, it's certainly no worse than algorithm number 1, because it's recursing less. You might even conjecture that it's somehow fundamentally better. It seems like maybe it's a big deal to be branching off subproblems at sort of only 75% the rate. But similarly, we know like the best we could hope for this thing is n log n, right? So we know merge sort has a better recurrence, and its running time is n log n. So if we were super optimistic, we'd say maybe this is n log n, but because it's 50% more recursive calls, we might be worried that maybe it's not that good. Okay? So all we know about algorithm number 2 is it's somewhere in between merge sort, which is n log n, and algorithm number 1, which is who knows what. All right? So that's where we stand. That's where we stand pre-master method.